So I'm here in Puerto Varas, Chile, in front of a beautiful lake whose name escapes me at the moment. It's a little bit it's a little bit crowded, but I'm attending a very interesting conference that has a lot to do with the onset of the Rubin Observatory that's supposed to be doing routine science by May of next year, and we trust that it's going to. And I'm with a postdoctoral researcher, a astrophysicist who does a lot of statistics, has a math background. He's at MIT and the Harvard Smithsonian Center for Astrophysics. It's Alexander Gagliano. Is that
Perfect?
Okay.
That was great.
All right, thank you. So tell me, you gave an interesting oral talk yesterday, I believe. What was the gist of your paper?
Yeah, so I study supernovae. These are stars that end their lives in these brilliant explosions. We're getting better and better at finding these explosions, but a lot of the conversations I've been having recently is how can we use machine learning to better understand what we think we're going to see and what is most important to study while it's still bright enough to study well.
And is machine learning a form of artificial intelligence?
Machine learning and artificial intelligence are terms used somewhat interchangeably. Truth be told, I would argue that both of them are really just applied statistics, but they accumulate different amounts of funding. Artificial intelligence right now accumulates a great deal of funding, so people like to use that.
There was a lot of controversy or discussion about what constitutes artificial intelligence here at this conference, and I haven't really gotten a straight answer, to be honest. How would you define it in terms of astronomy?
Yep. So I would argue that it's the use of data to allow an algorithm or a set of algorithms to do something that you don't manually hard code. So I want to set outcome from an algorithm, and I don't know how to get from my input to my output. Ideally, I want my algorithm to figure out how to take advantage of the data that I've given it to be able to generate the output that I want. And that training to get from input to output is empirical. So I don't write down a set of functions for what I want it to do. I just say, I want you to generate this output. That is machine learning.
And what do you mean by hard code?
So historically, algorithms were hard-coded, meaning that you would write a set of explicit steps for what you wanted a computer to do, one at a time.
Right.
First do this with the input data, then do this, and then you get your final answer. Now, our data is so complex that we know generally the types of outputs that we want. We know the kind of answer that we're hoping to get, but the data is so complex and so resource intensive to work with that it's really hard for us to explicitly hard code a set of instructions that are effective and really fast. So the hope is that we can use one of these models, a machine learning model, to be able to figure out those steps for us.
And there's a whole generation of new telescopes which are doing wide field surveys.
That's right.
And they're just inundating the field with so much data.
Yes.
And one of the biggest challenges for the LSST, the Vera Rubin telescope, which is a very wide field telescope, is that it's going to produce so much data that unless you have a plan to analyze this data in real time almost, you basically are what? You're not going to be using the telescope effectively, correct?
That's perfectly right. So to some extent, this depends on the type of science that you're excited to do. All of the data will be reduced and stored on the cloud. And even though this is a massive amount of data, there's some science that they will do afterwards to scan through that data, probably for many years afterward, looking for interesting things. But for supernova science specifically, the explosion is only happening for a finite amount of time.
Are you looking for type 1A supernova that are important for dark energy? Is that your bread and butter?
It is not.
Actually,
I'm interested in the explosions that we don't expect. The fact that we have a synoptic survey that's going to come online very soon means that we're now able to think about what we might expect to find that previous surveys were completely blind to. And so how do you generate an algorithm that is able to pour through terabytes of data every night and very quickly find things that you didn't expect? This is another reason why we don't want to hard code what we want the computer to do, because we don't know in advance what these new discoveries will look like.
So are you saying you're looking also for core collapse supernovae or what else? I mean,
Yeah.
Can you kind of give me a laundry list of what you're looking
Certainly,
for?
yes. So there are a range of new transients that we are starting to find that are given names that describe how they evolve in time, because we don't really understand right now what powers them. So some examples of these they're called rapidly evolving transients.
And define, for the reader, define transients, because
Yep.
that's kind of a broad term.
Sure. Anything that changes brightness in the night sky on a time scale significant enough for us to notice. So generally that's a year or less.
And that could be anything from a variable star to a comet.
That's right. That's right. All of it is transients. And in fact, at this conference, there are people who do solar system bodies to look for transients within our own solar system.
But the vast majority, not to put words in your mouth,
Sure.
of what I've heard here, people are excited about the supernovae, right?
Yes.
That's
I'm
that's
very,
probably
I'm
80
very,
or 90% of it.
That's 80 to 90% of this conference. I wouldn't say that's necessarily representative of the broader scientific community.
So thank you so much, Alexander. Enjoyed your talk, and good luck in the future. We look forward to hearing from you after the Vera Rubin is online.
Thank you very much.